Part 1, Spectrophotometry. In the lab this week, we'll use a method known as spectrophotometry to measure hemoglobin samples. The device we'll use in the lab looks very similar to the one you see on this slide, and this device is called a spectrophotometer. In this tutorial, we'll introduce you to the basic concepts of spectrophotometry. You'll learn how to apply Beer's law to calculate the concentration of a solution from the absorbance that you'll measure using the spectrophotometer. You'll also learn about how to determine the absorption maximum for a solution. And we'll give a few experimental tips for using the spectrophotometer in the lab this week. This slide shows a schematic representation of a spectrophotometer. And in this diagram, here's the sample that's being analyzed, and that sample is illuminated with light that's emitted from a visible light source. Now, visible light consists of a range of wavelengths. So the light is filtered here to select a monochromatic wavelength to shine on the sample. So by monochromatic, we mean only one wavelength. And some of that light will be absorbed by the sample, and some of the light will be transmitted through the sample. And that's dependent upon the color intensity of the sample. And the detector here will measure the absorbance or the transmittance of light. And in this lab, we'll be measuring absorbance, which we represent with a capital letter A. Now, the amount of light absorbed by the sample is proportional to the concentration of the solute in the sample. So by measuring the absorbance, we can calculate the concentration of that solute, or sometimes we call it the analyte, in the sample. And to do that, we'll utilize an equation known as Beer's law that we'll take a look at in the next slide. Beer's law is the basic physical law employed in spectrophotometry, and you may also see it called the Beer-Lambert law. It's based on the linear relationship between the concentration of solute in a solution and the absorbance of electromagnetic radiation or light by that solute. And Beer's law is based on this mathematical equation where I sub 0 is the initial intensity of light that illuminates the sample. So you can see that here on the diagram of the spectrophotometer. I is the final intensity of light that's transmitted through the sample. Epsilon is the molar absorptivity, and we also call this the extinction coefficient. The extinction coefficient is a measurement of how strongly a substance absorbs light at a given wavelength. And it's an intrinsic property of the substance, so it's going to be a constant value. L is the optical path length through the sample cuvette. So on the spectrophotometer diagram, you can see it's this length right here. This is L. And C is the concentration of the sample that's being analyzed. Now we know we can measure absorbance here using the spectrophotometer. And in this equation, absorbance is expressed mathematically by this part of the equation. Epsilon length concentration. So let's take a closer look at these three terms here: the extinction coefficient, the optical path length, and the concentration of the sample. The extinction coefficient is a constant that reflects the ability of a substance to absorb light at a given wavelength. And the optical path length of the sample cuvette is easily measured. So if you use the spectrophotometer to measure the absorbance of a sample, you can then use this equation to calculate the concentration of that sample. I want to mention that sometimes you'll also see absorbance called optical density, or OD. And I also want to talk about the units of absorbance. The units for the extinction coefficient are liters per mole times centimeter. The units for length are going to be centimeters. And the units for concentration are moles per liter. So take a look at this for a minute and think about the units for absorbance. You can see in this equation that these units are going to cancel out, and absorbance becomes a unitless measurement. So there are no units associated with absorbance. And the last thing I want to say here is that the extinction coefficient, which is a constant, is dependent not only on the molecular nature of the compound being analyzed, but also on the wavelength of light that's being used to illuminate the sample, or the lambda. So the next question to ask is this. When we're analyzing a sample by spectrophotometry, how do we determine what wavelength of light to use? To answer this question, we're going to talk about the concept of absorbance maximum, or lambda max. Remember that when we're using the spectrophotometer, the light source provides visible light, which contains many wavelengths. And the visible light is filtered so that the light shining on the sample is a specific single wavelength, or we call that monochromatic. Now, the extent to which a sample is going to absorb that light depends strongly on the wavelength of light. So the first task when analyzing a sample on the spectrophotometer is going to be to determine the absorbance maximum, or the lambda max. And lambda max is the wavelength of light at which a substance shows maximal or optimal absorbance. Now, the value of lambda max is characteristic for each specific compound, and it's important to know what the lambda max is for whatever substance you're analyzing in order to obtain the highest sensitivity of measurement. To do this, the absorbance of a sample is measured at several different wavelengths, and the data is plotted as absorbance versus wavelength. And using this plot, we can easily see that the absorbance for this substance is greatest at about 525 nanometers. So a wavelength of 525 nanometers would be used in any subsequent spectrophotometric analysis of this substance. And in lab this week, you'll do a preliminary experiment in which you'll plot an absorption spectrum to determine the lambda max for a sample. And I just want to note briefly, as you can see in the absorption spectrum seen here, that some substances may have more than one absorbance peak. And in these cases, the peak that shows the highest absorbance, which would be this peak here, is going to be what you use to determine the lambda max. Next, let's mention a few experimental tips for using the spectrophotometer in the lab this week. In the main experiment in the lab, you're going to utilize spectrophotometry to differentiate oxygenated hemoglobin from deoxygenated hemoglobin by the fact that these two forms of hemoglobin absorb light differently. And you'll need to keep in mind that deoxygenated hemoglobin will have a greater absorbance at 660 nanometers. So when you're doing the oxygen hemoglobin dissociation experiment in the lab, be sure you set your spectrophotometer to 660 nanometers. And to do that with this spectrophotometer, you would use these up and down arrow buttons here. The next important thing to remember is to set the spectrophotometer to absorbance mode. And if you're in the right mode, you'll see the A displayed here. One of the most common mistakes I see in the lab is that students are measuring transmittance instead of measuring absorbance. So if you see a T here instead of an A, you know you need to switch the spectrophotometer to absorbance mode. It's also important for you to zero the spectrophotometer between measuring each sample. And to do this, you'll use what we call a blank tube that contains a buffer or distilled water. So you'll insert the blank tube into the spectrophotometer, and then you'll press this button here, and that will set the blank to 0 absorbance. And remember, you must zero the readout with a blank tube between each and every sample you measure. So you'll be doing a lot of that in the lab this week. So these are a few other experimental tips to keep in mind. The spectrophotometer must be turned on for at least 10 minutes to warm up. So as soon as you come into the lab, and especially if you're in the first lab group of the morning, the absolute first thing that you should do is to make sure that the spec is turned on. Before you place any tube into the spectrophotometer, be sure to wipe the tube down with a Kim wipe. Any fingerprints or smudges on the tubes are going to interfere with your readings. If you can't close the spectrophotometer door completely, be sure to cover the opening with a dark cloth, and that prevents incident light from affecting your measurements. And finally, it's going to be extremely helpful and expected that you'll read through the experiment in LabTutor to familiarize yourself with the flow of the experiment before you come to lab. If you have any questions about this tutorial, please feel free to ask your instructor in the lab or to contact us through the discussion board.